So let's start with the first task, that is understanding the transformer. Here I won't be explaining the entire transformer architecture because there is a lot to that. And honestly, in the last 1 hour, I have read multiple blogs and watched multiple videos, which are extremely well written and extremely well formed. So maybe I will do is I can attach the links that I have read about the transformer, which explain it very well. For this section, what I want to do is to explain it, the transformer architecture, to you guys. This will be like an intuitive understanding only and just an overview. So this is the transformer paper that I'm looking at, and there is too much. Again, like I said, there is too much to the transformer architecture, but specifically we are considering the motion BERT. So the motion BERT contains obviously the only the BERT architecture. Instead of here as a multi-head attention, which is self-attention layers, and these are the vanilla versions. Obviously we will be having some variations of that, which we will discuss later on. But for this particular topic, we are discussing only the vanilla versions. So this will be our base for the entire journey, because the self-attention layers will be tweaked for temporal as well as spatial self-attention layers in later chapters. So we will be looking at that. So my goal is to understand attention equation. This is important because obviously it is the core of the transformer and how we use query key values. First of all, understanding what is query key value, and then understanding how this attention mechanism works. But instead of going too much into the maths, that how we are going to understand why only the softmax, why we are kind of normalizing it, why we are taking all of these three different sets of the matrices. We will be looking only at the intuition level, because again, like I said, there are multiple chapters we can look for, but I'm not the person who can teach you that well, because I'm again a learner just like you. I will be assigning some good blogs that I have read in the last few hours. So first goal is to understand this equation. So let's start with that tension equation. I'll be rewriting that equation first. So attention of query key value is softmax of the query key divided by the dimensionality of these vectors. Oh, sorry, the dimensionality of these matrices, and multiplied by V. So this is our equation. Sorry for the bad handwriting. So first of all, we need to understand what is the query key value. So from what I learned, it is like we can take an example of let's say a library. So whenever we go to library, we have a certain book, certain topic that I want to read about. Let's say I want to read about cars, and I go to the library and ask the librarian, hey, I want to read about cars. Do you have anything that I can that which can help me? So this would be our query, like, what do you know about cars? This would be our query. So this is query. Then the librarian, who knows everything about the library and who knows every book in the library, will go and search about the cars and the book about the cars. So he will be searching in the section, let's say, which is related to engineering. So I'm an adult, so he will be looking at the engineering, which is for, let's say, 25-year-old. Then under that section, he will be looking at uh, the book that I want to read. So he will be looking at a book. Let's say this could be a fiction. Oh, maybe not fiction because there are not many fiction books on uh, cars, but maybe something like as simple as a biography. Wait, sorry, biography or something related to engineering itself. So why I say biography? Because I have read um, How to Build a Car. You must read that book. That is a beautiful book if you are interested in F1. Anyways, so let's suppose I want to read this book, that I want to understand the mechanics of the car. Okay. So as you can see, while going into the library, he will be looking at these all factors, that there are many things that he will be looking at. He will be looking at this tag, the engineering section. Then he will be going to this tag, the age section, age by section, because I'm not a kid who wants to understand cards. So I won't be going into the kids section. I will be going into the adult section. So he will be looking at the adult section. Then he will be looking at if I want to, if I'm asking about the biography or about the engineering, like actual mechanics of that car. So he won't be going into the biography section. Let's suppose I want to go into the mechanics of it. So he will be looking at that. So these all things which I'm pointing out here, highlighting the engineering, uh, so the age group, the engineering, the biography or non-biography, uh, then this is the mechanics of that. So these all are which we can call as keywords, right? So these are the keywords which he will be pointing at, and he will be looking for these keywords. So maybe I will be providing this to him in my query itself. Like maybe I will be telling him like, hey, I don't need biography, need a biography. But maybe sometimes I maybe not using those keywords in my query itself. But anyhow, he will be looking at these keywords, and based on these keywords only, he will be able to understand what actual book I want. So these are simply called as keys. So these are the keys. And then when the things are looking good, value. So when he my query and keywords, those get combined and those are aligned, let's say, then I can go and look for the book. So whenever he is going into the library and combining my query and with the books, it has the entire library. So I will write this way. So the query that I have, query of me and um, the books inside the library. This all will be in his brain, and he will be combining these two things, and then giving me a set. So he won't be just giving me, let's say, of one specific book. or maybe he will be giving me one specific book. But what I want to understand is, what I want to point out is, he won't be just giving me one specific book. He will be giving me a set of books which may or may not align with my needs. So here we pointed out that, like I said, I want to have a book which is about the cars, and I never specified him if I would need a biography or not. But when he went into the library inside and was started wondering about which book I would be interested in, he is still searching for that specific section. So inside that, he will be, if I'm not giving him the keyword biography, he will be giving me entire this set. So there will be biographies or non-fiction, as in technical books, that he will be pointing it out. So there will be overlap. There will be something which is may interest me or may not interest me. But this is what value does. Value combines these two things. It tries to align my interest with the library. That is, aligns key key with query. Once again, from a technical perspective, query, key, and value. Query is something which I need. What do I want? Key is something for how I search. What do I have to search? Value is something which I have. So how many things do I have which are useful for you? These are the three things. So whenever we are, let's say, doing let's say text example, like a classic example. I speak Hindi, so I am dash dash. So this is the classic prediction example. So there are three things. I speak something. I speak Hindi. So I am. So these are the three things based on which I'm gonna predict the next word. So here, what will be the query? So let's say this is the first query. So I speak. What do I speak? This would be our query. So key would be inside the embedding space. The key would be like, what do I speak? What do I speak? So what type of things people speak? For example, they can speak a language. Also, there could be something as I speak if it's a human or non-human. So based on that, I will be considering if it's a language or not. Or maybe I speak, but I speak as in speak is a verb or a noun. Maybe not a noun, speaker, but noun. So anything like proverb. So how? in not for this example maybe, but in many other cases, I need to understand what type of word that I'm looking for. So that these kind of stuff. So this will be our keywords for that. But now we go into the value. So value would be our entire library, and what we have. What do I have? So based on this, if I have multiple things attached to this, I have, let's say, multiple things. For example, Hindi is a language, Marathi is a language, which is an Indian language. Again, English is a language, and so on. Then there are things like hu, sorry, human. So humans speak multiple languages at once, or multiple humans speaking, and so on. These would be our values. So I will be going into that. Um, so whenever we have the query, for example, let me just rearrange this in a better way. This would be our query, and this will be, I'll be rewriting that equation first. So attention of query key value is softmax of the query key divided by the dimensionality of these vectors, oh sorry, the dimensionality of these matrices, and multiplied by v. So this is our equation. Sorry for the bad handwriting. So first of all, we need to understand what is the query key value. In language, if I'm human, non-human, if it is a verb, noun, proverb, like what properties this have, properties this word have. So all of that these words have, and all of these things I will be considering for the next token. And then I will be looking at the value, like what type of things that I can predict, like what values actually can match with that. So these are the things I will be looking at. And as you know, this is not just about the one thing, like this is not just about speak word, but there are multiple words, like three things, like I pointed out, like which matters the most. So these will be the words. And for this we have multi-head attention. So most of the times what happens is, whenever we are doing the attention layer and we are performing the single attention, sometimes what happens is, instead of focusing on multiple contexts, like this one is very small example, so maybe one attention layer would be enough, one attention head would be enough. But what happens is, when we have the context which is pretty large and we have multiple things such as, um, let's say, I am living in Mumbai, I speak Hindi, I love reading, I am dash. So I'm just giving you example. So this is one thing, this is another thing, and this is third thing, and I'm predicting this one. So what happens when we are using one single attention head is that maybe, so maybe inside the attention head and inside this entire matrix multiplication, there is only focus on one specific part of the sentence, one specific context of the sentence. So instead of focusing on entire things, or maybe there would be something else. So for example, if I say, let's say, if I live in New York, and this is the sentence that I have. And if my attention head is just focusing on this sentence and not the entire context, so it will be predicting I live in US because New York is in US, and not he's not considering which language I speak or what type of things that I do. So maybe these problems arrive with one single head attention. So that's why we need multi-head to make it this one head. Second would be this would be second head, third head, and then we will be having the prediction. So this is why we need the multi-head attention. So yeah, this is the intuition understanding. So let's start with the implementation first. So as we know, these are the three things that we have, but these are implemented as matrix, query, key, and value. So let's say we are implementing in Pytorch, and we are understanding the linear algebra object. So now we know that. Let's go into the first example. So we already know that these things, as in the words, are passed as embeddings. So the vectors for words, these would be our vectors. So whenever we have any sentence, just like this, the similar first sentence, we have uh, entire matrix of that. So which is called as embedding for this. So in the original transformer, they are using the two types of embeddings. So first of all, the embedding, which is converts like the plain embeddings, and the second is they are also passing the positional encodings. I will get back to that. Why do we need the positional encoding as well? But for now, we need to understand only that this is the embedding space, embedding matrix that we are passing. And as I told you, there are three things that we need to understand about this. So what we will do is instead of passing, um, so we need these all three parameters as learnable. So let's say X is my input and input matrix, which is embedding and all of that, like positional and all the embeddings involved. This is my matrix. What I will do is then I need to find out the query, key, and value. So what I will do is instead of putting it into the X and all, we can use the matrix multiplication, and we have um, query vector, query vex, and then passed as X, key vectors, passed as X, and value weights passed with X. So this would be our linear operation. So inside this we have this matrix as a learnable, and um, which will be randomly initializing at first. So that would be our first thing to do. That is, it would be a linear operation and learnable parameter. So that will be our two things that we will be doing. So after this, we have the original equation, that is attention of u k v query key divided by tq and v. Oh, sorry, and softmax it out. So what we will be doing is we will be predicting this first. So if I look into that equation again, what we will be doing is if we have to look into this equation and again learn it from the intuitive level, I'm asking the query, then the librarian going into the inside the library and searching for the keys which I have provided or which it has already inside his brain, and he will be matching it out. So this is the linear first operation. He will be matching it out. Then we don't need this one first. So he will be matching it out. And then the softmax, what it does is it creates like so I need if I need a biography or non-fiction, or if I need a kids book or an adult book. So these all the things will be involved. So what softmax does is it will be pointing out at specific thing. Let's say a biography. So let's say a softmax will be pointing at the biography, and if it's aligning with me, like all the other things like kids, if I'm adult and all of that, it will be specifically pointing at that section of that. So softmax will be giving me a graph for that. So specifically like that. So we all know like the addition of that probability will be 1. But this is what I want to understand, that is to get the biography section, softmax will be giving me a certain direction. And then we will be going into what do I have, like what type of books we have, and then combining that with it. So this will be our second linear operation. So this would be our second linear operation, and this is first a single attention head. So inside the code, this should be very easy to just replicate it in multiple times and give the heads multiple heads. So that is not a big deal. But as I said, um, multi-head is really important. And one thing transformers are really good at scaling, that is you can put as many heads as you want and it will give you a better results with multiple heads, because as the context increases, like we explained here, as the context size increases we need multiple heads, and transformers are good at this because they work independently, like each head works on the different set, and then we can combine those after every head and after the every prediction. Um, then, I mean, we can increase multiple heads and all of that, but we also need to um, think about the GPU usage and everything which we have, because otherwise it will blow up the memory in the GPU and won't work very well. So that's why we need to understand the GPU usage as well. So there are like things like number of heads and all of that, batch size, which we will see in the code itself. Um, this is the coding section that we need to do. So I guess this should be enough to understand the transformer architecture better. So we will started with what is the intuitive understanding. We went into how the language model performs, and then we saw how we are going to implement it inside the Pytorch or any code that we will be doing. So I guess this should be enough. So let's start with the implementation of attention head. So I have implemented it already, and I will be explaining it on the fly because there was too many things that I wanted to understand. And to be honest, it is not fully written by me. I had to take some help from ChatGPT and other things. So I will be explaining what I've learned. So this is the multi-head attention like we talked about. So there are two things that go into it. That is the embedding dimension, like the dimension which we want our query key value vectors to be, and the number of heads that we just discussed. So how many number of heads? So based on my GPU size, I can decide how many number of heads that I want. The more number of heads that I have, Usually it is better for the prediction, but yeah, that would be our two things that we will need, that is embedding dimension and the number of heads. So first thing is like I need to understand the head dimension. So one thing that we need to be clear about is that when passing this entire key, query, and value weights, we are dividing it into multiple heads. And that is also true that we are using one single thing, one single weights for the each head. So that's why we are getting multiple updates. As we are using multiple heads, we are updating the similar weights in a multiple formats. So that's why we are contextualizing the context very well, because we are using multiple heads. That would be our goal. So these are the just initialization. So linear layer is just an operation. Like every matrix multiplication is a linear layer. So that is the weight initialization here. And um, not weight initialization, this is just matrix multiplication. So I'm initializing the matrix. And so this is like a embedding dimension, head dimension. There is number of uh, embedding dimension divided by number of heads, and then there is number of heads. So these are the things that we need and that we have initialized already. Then coming into the actual operation, we have the x as the input, which is the embedding space that we just discussed. And then we will be just dividing it into three things like batch size, the length of the text, and then the channels that we have. So here I'm not focusing on the channel first, but that way will be taken care of the code itself. But these are the things like batch size, number of heads, I'm sorry, not number of heads, it is the length and the channels. So after we have the weights initialized, now we just need to multiply our x, just like we discussed, with our weights. So this is the operation that it performs. This is happening at across the three things like query, key, as, and value. Our embedding space, our embedding is just getting linearly transformed into three other things like X, values, keys, and queries. But as we are discussing, there is one thing that we need to do is to transform it into something which is multiplicable. So we are viewing as in transforming the matrix into batch, then I mean batch size, length, and then we are dividing this channel into these two things. Like we are combining this third dimension into number of hits and number of by number of uh, head dimension. So that is what we are doing. So this was a three dimensional. This is now the fourth dimension. That is, we are dividing the third dimension into two more dimensions. That is like a simple operation that is performed by view, and we are doing this for all three things. And then we need to permute it. So I will explain it later what we the why we need it. But let's this is the first thing. Then there is second thing, that is we need to perform the first operation. So let's, if we go inside the attention itself, this is the first operation that we have before coming into the value, that we are combining query and key and finding out what type of things that we need. Like I said, the relevance of my query and the keys that the librarian has, and if we understood what I actually want. So that is what we call the score. So score is like something which is the librarian has thought about the books and I have thought about my books, and if we are on the same page or not. So that would be our score. Now the librarian will go and then combine with the value, like the actual books in the library. So that would be our next step. But for the scores, we are combining queries and keys. So like us, like here as well, like we have the query and keys transpose, and then we are dividing it with the dimension. So just the normalizing. So not the normalization, it is scaling actually. So that is the scaled up product. So here we have the queries, the keys, we are transposing the keys, and then we are multiplying it with the uh, this one. So we are dividing with the head dimension and root of head dimension, not just the head dimension, but the root of the head dimension. So this will be our score, that how aligned I am with the librarian. And then our final step is just to apply, after this, we need to apply the score at softmax to this. And then the final thing only remains is the combining with a value. So this is the last operation. The only thing that now we need to understand is to understand what is happening inside the permutation and how is the linear algebra is working on. So I will be just putting out the shapes of this. So you can see that before the permute it is like um, this here. Before the permute it is just so before going into that we need to understand what I'm passing here. So X is my input and this is where just one batch. If you see here, this is batch, length, and channels. So this is one batch only. I'm passing this is the length. I'll specify this. It is this figure coming from the motion board paper itself. So I'm putting it out as 246 specifically, and these are the number of channels that I have. So this is the second thing, and as well this is as well coming from the motion bird paper. 17 is the number of key points that we are tracking inside the human body, and then we will be combining it with multiple frames. So there is, like, let's say we are contextualizing multiple frames at the same time for 17 key points. So let's say we have two frames and 17 key points, so 17 by 2, that would be our um, contextual information that we will need. So that will be our input, and I'm passing this to multi-head attention that we have just described. And so there will be like batch size is 1, number of length, the length of that context is 246, and then 17 by 2 is my channel dimension. So this is even happening here as well, like for example, yeah. So when we are reducing the third dimension into two more dimensions, there is number of heads and head dimension as well. So as I'm passing number of heads to be 2 here, so this will be get combined into 17 by 2. So this is 1, that is the batch size. This is the next n, this is the length, number of heads 2, then 17 is the dimension, embedding dimension, head dimension, sorry. So that would be our head dimension, and then we are permuting it to 1 2, like this one will come here and this will be get permuted. So these are the dimension that I have after that. So if we just go inside this, we are okay. So let's suppose if I print piece transpose shape, yeah, so it is the what I want. So I want to understand what is happening inside this operation itself. So let's see that output. So this is the transpose operation, and let's suppose I'm printing out query shape as well. And this is transpose operation. Wait, I want to understand. Yes. So this is what I want. Um, so inside this operation, like is queries into transfer operation, this is what happening. Like this is the query vector,
uh, sorry, query matrix, and this is the key matrix, which is transpose, and we are combining this at the, I mean, we are multiplying it in transposing at last two dimensions, like 20, 246, 17, and 17, 246, which are head dimension, head versus number of heads. Sorry, not head dimension versus the, so inside this we are combining, this is the actual output that I want, that is query and transpose, and inside this we have 246 as our length, 17 as our head dimension, and inside that when we are performing this operation, what we are doing is we are combining, we are multiplying at these dimensions. So this is how we are combining the context of that length over the multiple heads, uh, over the head dimension. So this is the score that we are performing. I won't go too much detail into this matrix multiplication because that is actually yet another video that you can we I can make. But what I understand, it is 246 by 17, that is the length, versus the uh, here we have described head dimension, and we are combining the head dimension, I mean each head dimension, with the contextual length, that is the 246, the n of our multiplication. So based on this embedding space, we are we are combining queries and keys for each head dimension at every uh, contextual length. So that will be our first operation, first linear operation. Then we are just performing the scaling that is based on the head dimension. After this scores, we have the softmax operation that we are performing, and only then we can combine this with the values. So if we have, let's say, attention shape and value shape, let's do that as well. So yeah, so we have the attention for, like I said, 246 by 246, because we are combining queries and keys for each contextual length. So we, after performing this operation, like 246 into 17 by 246 by 17 into 17 by 246, the actual output would be 246 by 246. So this would be our attention size, that is 246 by 246. Essentially what it represents is each uh, with each word inside our total context, how it is getting combined, or how it is attempting to some other word. So if there are 10 words, this would be our 10 by 10 matrix, but our contextual length is 246, so it is 246 by 246 matrix. Then we have the values. So this is like a librarian now going into the library and asking for which books that I can actually read. And then I'm combining this with this. So the output would be 246 by 17. So that would be my actual output, like output shape. But this will represent that I will have now, when I have the entire context in my head, now I'm just combining that into number of heads, that is, or not number of heads, into the head dimension, that is 17. So what where we started was, we started with the queries, where we have the context and the head dimension, the keys. For the first operation that we perform is like, we are combining the head dimension. I mean, we can contextualize the entire embedding space with along with the head dimension. Then we are combining, we are extracting only those head dimensions which are actually relevant. So that would be our values, and that is why we have the 17 as an output inside that. So hopefully this is clear by now.
I mean, at least it is clear to me. This is my first thing that I need to understand that matrix multiplication, like from not just only from the linear algebra perspective, from the perspective of intuition as well. So I want to understand how and why it is working. Maybe that will be our next step, but for now I'm satisfied with this answer, that is how these performances are done.
And we have performed the attention score as well. So the next step would be to understand the actual implementation of the motion bird paper. That is, they are performing two separate forms of uh, attention, that is spatial and temporal. So there is slight variation inside. I think this implementation has nothing to do with our base structure, but it is to do with the how we are passing the data input to it. So that way will be our next step. So I will be performing that. Hopefully this was helpful and wasn't that chaotic. But if it was, this is true because my head is absolute chaos and learning is chaotic. So that is why I'm making these videos, just to make my thoughts clearer. So hopefully it was entertaining for you. See you next time.